This is the second video out of 3 covering verifying trigonometric identities. So let's verify that sine of alpha plus beta divided by cosine alpha times cosine beta is equal to tangent of alpha plus tangent of beta. Well, I always like to think about what has to happen algebraically to get from one side to the other. I'd be inclined to start with the left side because the argument in the numerator of the left side is alpha plus beta. I typically start on the side with the more complicated argument. And algebraically, we're going from a single fraction to 2 terms that aren't fractions. Well, if I'm going to go from a single fraction to 2 different terms, that means that my numerator is going to have to transform into multiple terms. We're then going to break it up into multiple fractions and simplify each of those fractions. That's what has to happen algebraically to go from a single fraction to 2 terms being added to each other. I also feel like since we're starting with sine and cosine on the left and we're ending with tangent on the right, that I'm betting that my second to the last step is going to be sine alpha over cosine alpha plus sine beta over cosine beta to get me that tangent of alpha plus tangent of beta. So let's start with our left-hand side, and we need to figure out how to get multiple terms out of that numerator. We also need to get from an argument of alpha plus beta to arguments of just alpha and beta. So we want to use our sine sum formula. Sine of alpha plus beta is equal to sine of alpha cosine of beta plus sine of beta cosine of alpha. And then our denominator stays the same. So there we have our 2 terms in the numerator. Great. Well, we need this to simplify from a fraction to not a fraction anymore. So we want to split it up into 2 separate fractions with a denominator of cosine alpha cosine beta. That's sine of alpha cosine of beta over cosine of alpha cosine of beta plus sine of beta cosine of alpha over cosine of alpha cosine of beta. Now let's see what simplifies. In our first fraction, notice that we have cosine of beta over cosine of beta. Those are going to cancel out and leave us with sine of alpha over cosine of alpha. And then with our second one, cosine of alphas are going to cancel out on the top and bottom, leaving us with sine of beta over cosine of beta. And we know that sine divided by cosine, as long as the argument is the same, turns into tangent. So this becomes tangent of alpha plus tangent of beta, and that's our right-hand side. Again, notice with these identities, we're always starting with one side and showing that it equals the other side. We're never working both sides of the equation here. Let's try another one. Let's verify that secant of theta minus tangent of theta quantity squared plus 1 divided by secant of theta cosecant of theta minus tangent of theta cosecant of theta is equal to 2 tangent of theta. Well, as soon as I look at this, I say a bunch of stuff has to cancel out. To go from that really complicated fraction on the left-hand side to just 2 tangent, there has to be a lot of stuff canceling out. And I'm also wondering whether or not I want to turn things into sine or cosine. I'm leaning towards no, because neither side has sine or cosine. So I would leave everything in terms of tangent, secant, and cosecant, and hopefully a bunch of stuff is going to cancel out, and then we'll be left with just 2 tangent. We're definitely starting on the left side. That's our more complicated side. So let's think about what to do with this. Well, I have a binomial squared in the numerator. That's secant minus tangent quantity squared. So we're going to want to write that twice and multiply it out. And don't forget that plus 1 then off to the side. Then we have our whole denominator still. So let's multiply there in the numerator. Secant times secant, that'll be secant squared. Secant times negative tangent, that's minus secant tangent. Negative tangent times secant, that's minus another secant tangent. And you could write that tangent secant if you're more comfortable with that. It's still going to be a like term. And then a negative tangent times a negative tangent plus tangent squared. And we still have that plus 1 on the end over our entire denominator. All right. Well, I feel like a bunch of stuff is going to have to cancel out. That's the only way we can simplify this fraction to not a fraction. And with fractions so complicated like this, technically they're rational expressions, the only way we can simplify these fractions is by canceling common factors. So I have to get this to a form where I can factor it. Looking at the numerator right now, well, I guess I have some like terms there that I can combine. Right, we have negative secant tangent twice, so I can rewrite that as minus 2 secant tangent. And then I want to talk about this tangent squared plus 1 here. One of our Pythagorean identities states that tangent squared plus 1 equals secant squared. So I'm going to replace that tangent squared plus 1 with secant squared. All over my denominator. We now have like terms again in the numerator that can be combined. I have these two secant squareds. So this becomes 2 secant squared minus 2 secant tangent all over my denominator. And now we have a fraction that looks a little bit more manageable to try to factor. So let's take a look at our numerator there. See if that can be factored. And it may be helpful to do some side work. So over here on the red, I'm going to strip out the trig so that it helps us see the algebra. We have 2s squared minus 2st. So how could we factor that? Notice that we have a common factor of 2s. And if we factor that out, we're going to be left with s minus t. So that means that we can factor our numerator, taking out a 2 secant, and then we're going to be times secant minus tangent. So there's the numerator. Now let's try to factor our denominator. So I'm going to do the same thing. I'm kind of going to strip away the trig. So we have s times c minus t times c. There, I see that I have a common factor of c that could be factored out, leaving us with s minus t. So that means that our denominator can be factoring out a cosecant. And then I'm left with secant minus tangent. Well, look how nice that worked out for us. We now see that we have a common factor of secant minus tangent in the top and in the bottom that can be canceled out. We're left with 2 secant of theta over cosecant of theta. Now remember what we're trying to get to. We're trying to get to 2 tangent. So right now that doesn't look exactly like tangent. So I think what I'm going to do is I'm going to rewrite this in terms of sine and cosine, and see for tangent I need sine over cosine. See if this will simplify to be sine over cosine, because I already got the 2. Alright, so I'm just going to leave the 2 out in front. And then deal with this secant over cosecant. So secant is 1 over cosine, and cosecant is 1 over sine. To simplify this complex fraction, because it's just 1 fraction over 1 fraction, I'm going to multiply by the reciprocal of the second fraction. So this is going to turn into 2 out in front, and then 1 over cosine times sine over 1, and look at that, there's our sine over cosine. This ends up being equal to 2 sine over cosine, which is equal to 2 tangent, and there's our right-hand side. That was a long one. But we just take our time, multiply things out, replace so that we can factor. I think it's really important to think about the algebra behind the identity to help you make decisions. There's one more video on verifying trig identities. Make sure you watch that 3rd video.